So let's look at a simple example which demonstrates the usefulness of a MaxEnt objective or a MaxEnt objective in order to perform, to transfer knowledge. So let's say that we have this task here. We have an ant robot that needs to get to some goal location. And learning a low entropy task would be just to reach the destination as soon as possible. A high entropy task will allow the robot to learn to go either through this path or maybe with a lower probability, but also to have some option of going through the other path. So that will be a multi-mode policy, a policy that knows about two different solutions, right? Why is that helpful? Because let's say that our task changes or we get a new task which is very similar to the old task, only now we added a blocked, the top path is blocked, right? We added some kind of an obstacle there. And imagine what would happen, or how long will it take us to train our previous robot on the new task if we would have learned a low entropy policy, this before. We'd have to, so if we pre-trained it on a low entropy policy, we'd have to let it forget or learn that these Q values for this path are wrong, either Q value or the policy for going up or going through this path is wrong. It leads to the blocked to a blocked path, and so that might take some time until it learns that, and then until it identifies or discovers the new path. However, if initially we would have trained it for the maximum entropy policy, that is, it knows about, it has some notion of these two paths, then intuitively we can see why it would be easier for it to adapt to the situation where this top path is blocked and to quickly rediscover, or it's already discovered, but reinforce the bottom solution. So let's see some demonstrations of this. So this is just a video showing three types of pre-training. One is just no pre-training, so for the new task we'll just do random initialization. A second, one second, oops, this went too fast, one second, let me go back. Okay, second baseline would be DDPG initialization. DDPG is, why was that chosen as a baseline?
Because it's deterministic and struggles with exploration?
Because it's a low entropy, right. It's a low entropy, DDPG results in a low entropy solution, right? And so in this paper they actually try to show that soft Q learning, as we saw in the previous topic, leads to a high entropy policy. So this is why they chose these three baselines. No initialization, low entropy initialization, high entropy initialization, okay? And so for the initial task, they just allowed the agent, I think the reward was just to progress as much as possible in any direction, right? It's a very simple initialization, but it allows the robot to generally understand how to move in this space. So let's continue and see how it performs on a new task. Okay, so now they perform fine-tuning on a specific task which is progressing in a very specific direction along a hallway. Previously it could just go in any direction, now it has to progress in a very specific direction. Okay, so now you can identify that the random initialization, so no pre-training, you can see that it doesn't perform very well compared to the two other approaches that do use initialization. However, at this point it's a bit hard to identify oh, no, it's less so. It might still be a bit hard to identify which one of these, the low entropy or high entropy, is better. But don't worry, soon I'll show you the training curves for each of those. Okay, but as we perform more and more training epochs, we can actually see, can we?
They're about the same.
They're about the same so far. Eventually, oh, here we go. So the soft policy initialization, we can see that it does perform generally better. Again, this is a new task where it doesn't just go straight, it needs to go through some corners, yeah, a new shape. Oh, and here we can see that it's actually even better to be with higher entropy initialization. And these, by the way, these demos are from Sergey Levin's group at Berkeley. Just giving credit. So indeed, the conclusions are that high entropy initialization, MaxEnt initialization, results in better initialization, better learning on the new task compared to deterministic policy initialization. But we already saw that, right?
I think it's replaying it.
Oh, no, I don't want to replay. Okay, so let's see the actual results, see the actual learning curves. So this is from the paper that discusses the transfer learning with entropy maximization. So here at the bottom you can see the training curves for 3 different target tasks, right? Either wide hallway, narrow hallway, or U-shaped maze. And you can see the different types of initialization, where the orange line is the random initialization, so no specific initialization. Then we have the green line as DDP's G initialization, or again, this would be a low entropy initialization, and a high entropy initialization, a MaxEnt initialization. And indeed, as we saw in the video to some extent, we can see here more clearly that learning on the target task, on the new task, given different initialization techniques, performs or results in faster learning when we do maximum entropy initialization. Any questions?
So,
seems reasonable.
Even if we have high entropy randomly initialized policy, if it's not been pre-trained, it might not necessarily help.
Oh, that's a good question, right? So the random initialization, the randomly initialized policy can have, or usually is, it has very high entropy, right? It's almost uniform, goes all over the place. So in many cases, the randomly initialized policy will have higher entropy than the MaxEnt entropy initialized policy. So how come the MaxEnt is still performing better than the random one?
Because it's also maximizing the returns.
Because it also learns something valuable, right? So yes, it is high entropy, but it also has some notion of how to get the robot moving around, right? It has some valuable information. So it retains the valuable information while trying to be with high entropy as possible, right? So it is a balance, right? It's not just, okay, try to maximize the entropy. No. If we go full entropy, uniform distribution over the actions, no, we don't transfer any useful knowledge. So right, we'll have to balance it. Balance the transferring the knowledge and maximizing our entropy.